Hi guys, we are back in chapter 20. This next little bit, and this is actually the end of the chapter, has to do with a little bit of math. So yay, math day, fun day. And but then also some of the ways that this concentration that we're going to talk about today affects solutions. So first of all, concentration deals with the number of solute particles that are dissolved in the total solution. So how much solute is in, how much solvent. And two terms that you guys are familiar with are a dilute solution, which means there are fewer solute particles, or a concentrated solution, which means that there are more particles. So if we're going to go back to our Kool-Aid example, a dilute Kool-Aid solution, you guys have all had them, tastes mostly like water. You might have a little bit of flavor in there, but it is so little Kool-Aid that the water is the kind of the overpowering taste. Concentrated is when you dump, like half of the jar of Kool-Aid powder into your cup of water, which makes it really, really, really concentrated. Lots of flavor, probably kind of thick, and just more particles compared to the water. Now, the math that goes along with this, we will talk about it here, but I will do some example problems at the end of this, this little section of notes. And then one of the days this week, you will do some math problems. The way that I work the problems towards the end of these slides will be the way that I want you to work the problems that I give you for practice. So we'll do more on that in a minute, but I do want you to know that for concentration, for us, kind of day-to-day stuff, a lot of the things that you have that are solutions are actually measured as mass percent. And so what that is telling you is the mass of the solute in grams, that a lot of times they set it kind of equivalent to 100 grams of the solution. So for example, if you have a 10% salt solution, so if I have a cup of water and it's got salt in it and it's a 10% solution, that means that if I had 10 grams of salt and I added them to 90 grams of water, that would give me 100 grams of this solution. And so the total numbers, so the 10 and this 90 over here, equal to that 100. And so it's just the grams of solute plus the grams of solvent. Now, that's nice and easy, and we will use some of that later, but it will be a little bit more than that, the problems that we work in just a little bit. Now, another concentration unit that I want you just to have heard, we won't do any of this math because you'll do a lot of it when you guys take chemistry in a couple of years, is molarity. And molarity is the concentration that is determined for a solution, and it is based on the number of particles within the solution again. But now, instead of being grams, they use a unit called moles. And we haven't talked about it a lot, but you guys have seen the moles, the stuffed moles in my classroom. You guys have also seen like the cartoons that I had next to the smart board earlier this year. And a mole is the SI unit for the number of particles. And it is basically there to make the math a little bit easier. And a man named Amedeo Avogadro established this. It's a mathematical constant, and he said that 1 mole of a substance is equal to 6.02 times 10 to the 23rd particles. So it is a lot of particles in 1 mole. So if you can imagine the number 602 with 21 zeros after it, that's how many particles there are in 1 mole. And so when you measure molarity, you are measuring the moles of the solute versus the liters of solution. Now, in a lab setting, most concentrations are measured in molarity. In a real world setting, it's that percent mass that we already talked about. I just wanted you to have heard what molarity is. You'll do lots of these problems in a couple of years again, but just kind of be aware. Okay, so now with these solutions, there are some things called colligative properties. These are properties that change for the solvent. So in our case, usually water. These are properties that change based on how much solute you put into the solution. So the main two colligative properties are boiling point and freezing point. And for the boiling point, the boiling point is always elevated. So that's where they get this boiling point elevation. That means that when you add salt to water, it raises the boiling temperature. So you guys, I hope, know that water normally is going to boil at 100 degrees Celsius. That's a 1 there. 100 degrees Celsius. But if I take my 100 grams of water, for example, and I add those 10 grams of salt, then instead of boiling at 100 degrees even, like pure water should, it will boil at something more like 102 or 103. It's not a huge change, but it's enough to be measurable. It is enough that that it makes a difference as far as how long to heat it or those kinds of things. You'll hear people say that adding salt to water will help pasta cook faster. You'd have to have a lot of salt to really make a difference in the cooking time, but it is a true statement. And so this little arrow here, so the added solute particles interfere with the heat needed to change the liquid molecules to gas. So the interfere basically means they're just kind of getting in the way, and they are not allowing it to evaporate or to boil like it normally should. Now, freezing point depression, that means that the freezing point is going to get lower. So same thing, if I take my water and I add some salt to it, and then I stick it in a freezer, instead of freezing at 0 degrees like water should, so 0 degrees for pure water, it would have to be more like -2 or -4, whatever it is. And so it would lower the freezing temperature to have to be colder in order to freeze. This is why they put, or Mr. Fratsky a lot of times out in the parking lot, if it's icy at school, he'll put kind of those like little blue crystals that you see. Those are not necessarily salt, they're chemical salt. And so what they do is they interfere with the structure of the ice molecules as they're trying to bond together, and they just kind of get in the way, and they don't allow the water to freeze until it gets even colder. And so it is, again, a useful thing if you're trying to prevent slick spots with ice or that kind of thing. It's also what they do when they make like homemade ice cream, and they put rock salt down into the container. If you guys have ever seen rock or homemade ice cream made, and it has a little crank, and you turn it and turn it and turn it, and so it is actually a little bit colder than 0 degrees, and that helps the ice cream form faster. So useful thing to know. And then one more property of solutions is osmotic pressure. We won't talk a lot about this after today, really, but osmosis, you probably have heard, is when a solvent moves from an area of high concentration to an area of low concentration. Usually, again, we're talking about water here. So with this solvent, we're dealing with water for the most part. And water will move from an area that is almost pure water to an area that has less water, and this is called the osmotic pressure. And it will move through a semi-permeable membrane, and so this membrane will allow the water to pass through, but not other particles. These little kind of U tubes that are there on the screen, the yellow dots are pure solvent, so that's like the pure water. And then over on the other side where it has the bigger purple dots, that is a solution. So you have, I'm going to put pure over on this side, so pure H2O. And then over here, this is where you have the solution. So what happens is there's more water over here. So here is all the water, and water, because of osmosis, will move to less water, to an area of less water, in order to try and balance everything out, or at least balance the water concentration. And so what will happen is you will develop or produce what is called osmotic pressure. And that is the amount of force that is produced as this solvent, as water, is moving across this membrane. And so it builds up this pressure, and then the amount that it actually kind of raises the water level by, that is, I'm going to put OP here, that is the osmotic pressure. So again, it's measurable. Your cells tend to deal with osmotic pressure quite often, and they are moving things in and out as water is moving in and out. It's one of the things that your cells really rely on as far as like staying hydrated or having enough water or not having enough water inside the cells. Your cells don't work well without enough water, and so this osmotic pressure can be very important as far as their function. Okay, so now here we are to the problems that I mentioned earlier. With these problems, I want you to, I think I'm going to give you the practice problems for the math on Thursday. I want you to go back and look at how I'm working these problems, and I want you to work them step by step the way that I'm going to show you to make sure that you kind of know what you're doing. And some of this is going to be basic algebra, some of it is going to be just basic math. So follow with me. We'll have, our own individual fun day math day here, and then you'll get to do one on your own on Thursday, you lucky kids. All right, so here we go. The percent by mass problem number 1. So it says you must prepare a 15% by mass solution of sodium hydroxide in water. Sodium hydroxide, you don't really need to know this, but just so you do, sodium hydroxide is NaOH. All right, so we're mixing in sodium hydroxide with water, and we want it to be a 15% solution. So if you need 100 grams total, how much sodium hydroxide would you need and how much water would you need? So there's actually 2 problems here, one for 100 grams of solution, one for 75 grams. So first things first, your first step is going to be to change your percent to a decimal. In order to do that, you would take your 15% and you would move the decimal, which is right there, you would move it back 2 places. So as a decimal, 15% would become let me get a point on there, 0.15. And then I'm going to take that 0.15 and I'm going to multiply it by the total amount. So I want 100 grams of this total, but I want to know that 15% of it is the sodium hydroxide. So 0.15 times 100 gives me 15, and that is going to tell me that I need 15 grams of NaOH. All right, so there's my first thing. So there's the sodium hydroxide, 15 grams of it. Then it wants to also know how much water do I need. So for the water, I would take the total amount that I want, which is the 100 grams of solution. So that is from here. And I know that 15 grams out of that 100 is the sodium hydroxide. And so that means that whatever is left, if I subtract those two, will be the water. So 100 minus 15, put that in your calculator, and you should get 85 grams. And this is 85 grams of water. So putting those two things together, 15 grams of NaOH and 85 grams of water would give me 100 grams of a solution. And because I figured the 0.15 in there for the 15%, I know that it is a 15% solution. Okay, so the steps are to change your percent to a decimal, to multiply your, so here's that one, so percent to a decimal, first step. Second step is to multiply your decimal times the total, which is 100 grams. And then my third step is always going to be to find the water, and that is going to be to take the total minus the grams of solute, so in this case the grams of NaOH. Okay, so 1, 2, 3, 3 steps. Okay, so now we have a second question on here. How much if I needed 75 grams of solution? So I would do the same thing. We've already gotten step 1, so we know that we're going to use the 0.15 because I still want a 15% solution. Come here, Dot. And now, instead of multiplying it by 100, I'm going to multiply it by 75. And 0.15 times 75, oops, hang on, I wrote it down over here. 0.15 times 75 is 11.25. And that's grams of NaOH. Okay, so that's how much of the solid I would need. And then to figure out the water, same thing, I would take the total that I have, which is 75, and I would subtract 11.25. So 75 minus 11.25, my answer's over here, should be 63.75 grams of water. Okay, and so the two different problems, so here's the first one. And so that's what I would need if I wanted 100 grams. And then this one is what I would need if I would want 75 grams. Now, if we were all together, and I wish we were, we would do a lab kind of similar to this, and I would have you guys make your own Kool-Aid. And you would, instead of me telling you what percent you were going to make, you would make your solution and we'd measure everything, and then you would tell me what the percentage was of your solution, how much Kool-Aid you had dissolved in how much water. And so it's kind of interesting to see. Most people don't really like it as concentrated as they think they're going to like it, but this is a pretty common thing that you will see if you look at maybe the vinegar container that you guys might have in your house. It will say somewhere on there something like 5% acetic acid. Another one is hydrogen peroxide, and it is usually like 4% or something even lower. Contact solution may have percentages on there, but basically what they're doing is saying, when this was made, I took this much of the acetic acid and I added it to this much water to make your vinegar, or same thing with hydrogen peroxide. And so it is actually something that you see quite often, or that you use more often than you think. And now one more practice problem, and then I'll be done. Okay, so on this one, same kind of problem, so it's just follow the steps again. A 14% solution of sodium chloride, so sodium chloride is NaCl. Oh, NaCl, okay. In water has a mass of 200 grams, so there's my total. What is the mass of sodium chloride within the solution? So how much solute? And then what is the mass of the water? So step one, I'm going to take my 14% and I'm going to change it to a percent. Excuse me, to a decimal. And so I'd have my point, or I'd move my decimal 2 places, so I'd have 0.14. And then I'm going to multiply it by my total. So 0.14 times 200 for the solution. 0.14 times 200 is 28 grams, and that is of the NaCl. You're always going to find the compound or the chemical first, because that's what you're going to be adding into water. So if I want to make 200 grams of this, I would measure out 28 grams of sodium chloride, salt. And then if I wanted to know how much water, I would subtract. 200 was my total. I know I'm already using up 28 of it for the sodium chloride. And so when I subtract those two, the remainder is going to be the water, 172 grams of H2O. So those two together, and you can even check it if you wanted to. If I went back and checked, this would be 200 grams, and that's the total. That's the salt and the water added up together. And so that gives me my percentages. So follow these steps. We will do some practice problems, like I said, on Thursday. Your book has some practice problems, or probably has these same exact problems in there, or something like it, that you can look over. Please be sure and ask me questions if it doesn't seem like you're kind of getting it, and just kind of let me know how you're doing. Thanks, guys. Bye.